E 对。什么意思？再撑着走。
Maybe we'll hide it so that the other person doesn't find it. Okay, so it's my pleasure to welcome E.E. Tai, and she will tell us about stochastic error cancellation in analog quantum simulations.
Hello. Thank you for the introduction. I'm E.E. Tai. Today I'm presenting our work on stochastic error cancellation in analog quantum simulations. This is a joint work with Yutong and John Presco at Caltech. So to start off, as we all know, quantum computers can more efficiently simulate quantum systems compared to best known classical algorithms. A simple example is that we can see the exponential speed up in space and time when we want to simulate a 2D Heisenberg model, when we, under the assumption that each qubit is noiseless. Compared to its digital counterparts, the analog quantum processors do not need local control gates to perform informative simulations. So what does this mean? This means that in the analog case, unfortunately, compared to the gate-based digital quantum processors, it's less versatile. It can do less things. This also means we cannot implement error correction on this platform. However, on the positive side, these processors are also less susceptible to error. So between the digital and analog quantum processors, we see a trade-off between versatility and susceptibility to errors. Therefore, it's very important for us to address the following question in the analog setting. That is, what are the prospects for reaching quantum advantage using near-term quantum simulators that are not error-corrected? Specifically, it's very important for us to analyze how errors accumulate in this analog setting. So recently, Trivedi et al. Provided one of the first analytical results in error scaling in the analog setting. And what they did specifically is showing that local observable errors scales independently of system size, which is a really nice result. So our work directly built on top of their result. This is a brief summary of our contributions. First, we have a slightly different assumption of our local perturbations. So the local perturbations we have are assumed to be stochastic and statistically independent between the actual and target Hamiltonian. So with this assumption, we're able to obtain the following results, which are improved observable error bounds that hold with large probability. Specifically for any arbitrary observable, we're able to show a quadratic improved scaling of square root of number of qubits rather than the previous best case of linear in number of qubits. Next, we also look at this local observable setting in the thermodynamic limit, and we're able to show an almost quadratic improvement. An almost quadratic improvement with respect to time. So we have t to the d over 2 plus 1 compared to previous best known result derived by Trivedi et al. Of t to the d plus 1. Here, d is a dimension of the physical lattice space that qubits live on. And lastly, applying these results to the fidelity decay setting, we're able to show a non-exponential decay where the fidelity decays with respect to square root of n rather than linear in n. So this is really nice because we're able to get a non-exponential decay. And lastly, we provided numerical experiments to support these favorable scaling analysis. So before going through the results, I would like to first provide some intuition about how the cancellation process works. So first, let's assume we have m independent error sources, which essentially are modeling the qubit errors. If we say each qubit or each error source follows a Gaussian distribution with mean 0 and variance of delta squared, this means that the cumulative error is a total Gaussian error with, again, mean 0, but here, m delta squared variance. This means that the total error has a standard deviation of square root m times delta, which means that on average, we can obtain around order of square root m cumulative observable error when the number of error sources goes really large. So this means that if we fix the cumulative observable error, we can tolerate more hardware error. So a simple numerical example is that if we have x's following a standard Gaussian distribution, and we sum them together with n of them, take their absolute value, you can see this kind of square root scaling compared to a generic linear growth in n. So this is a general intuition about how the cancellations work. Next, I will talk about how the analog setting is usually set up. First, consider a Hamiltonian H that we want to implement on a physical hardware. The problem is when this H is implemented on the hardware, there will be some error terms introduced by qubits or sets of qubits. So we ended up implementing some sort of H prime, a perturbed Hamiltonian, on the physical platform. So the difference between the ideal and perturbed Hamiltonian are made up of these local terms, which characterize delta, which characterize local perturbations, and we sum over n, which is all the qubits in the system. So this is a very generic setup for the analog setting. Based on this setup, we have our slide assumption for the local error. So instead of the local error being a constant delta, we make it a random variable that follows the following distribution. So we define these GI terms that follow what we call a generalized normal distribution, which is also called chi-deformed Gaussian. So here are some properties of this chi-deformed Gaussian that are very useful for our results. First, this is this GI term is in term of a Gaussian, so we're able to generalize it from a Gaussian. Next, we want to restrict the variance of this random variable, GI, and we want to keep it unbiased. Lastly, we want to make sure it's bounded, just like how physical noise is bounded in a system. So with these assumptions, we're able to have uniform distribution over an interval and truncated Gaussian distributions as potential distribution that GI can follow, which is really nice. So next, this is our main result. So first, if we have an arbitrary observable O, an ideal Hamiltonian H, we time evolve it, and with respect to the initial state rho, and we take the trace of it, so we average over this observable value over time. And we want to see how much this observable value differ when it's under the target Hamiltonian H and the perturbed Hamiltonian H prime. So here, n is the system size. With this bound, which is with the leading order term of square root n, t delta, where delta is a characterization of the local error, we're able to arrive at this bound. And here, in order to have time scale in which simulation provides meaningful results, we assume the leading order term is less than 1. And this is stronger than the previous bound that scales linearly in number of qubits when we assume that the GI terms is just simply a constant, which means there's no error cancellation. So next, I will provide a brief sketch of the proof on how we got to this result. So first, we want to show that how much the average observable differ. So we average over multiple instances of the noise, which is give us this expectation value with respect to GI terms. And we want to see how it differs from the ideal Hamiltonian time evolution. Here, it's very important that the leading order term is second order rather than first order. So with this result, we shows that in order to achieve meaningful results, we only need local perturbation with order of 1 over square root of n, rather than the previous naive result of 1 over n. Again, quadratic improvement. So now I'll provide a brief sketch of how this proof works. Quick reminder, this is how we relate the H prime and H with the GI expressions. Next, we use interaction picture to relate the time evolution under the ideal Hamiltonian and the perturbed Hamiltonian. Then we perform Dyson expansion. So we get all of these time-ordered integrals. And then we take expectation value first with respect to rho, the initial state, then average over GI. The key part, though, of this long expression is this expectation value part, where because the way we define this GI as the chi-deformed Gaussian with certain properties, if the number of GIs being product is odd, then we have 0. So this is how we get the leading order term to vanish and only have a second order scaling. Now, to get to the second part of the proof, the initial bound we have, we want to prove the square root scaling. So what we want to show is how much the observable expectation value can deviate from its average. This is simply a direct application of concentration of probability measure. Because the way we define GIs is in terms of a Gaussian, this means that we can apply this Gaussian concentration equality for Lipschitz functions. And this gives us, using a triangle inequality, combining this bound and the previous second order bound, we're able to get our main result with leading order terms scaling with square root of number qubit times time times delta. Next, we're also very interested in tasks that have observable values that scale independent of system size. Because these are tasks that analog quantum simulators can conceivably run in the near term. So one task of interest is local observable because itself is independent of system size. So this is how we set up our local observable setting. We consider a spin system with spatial locality on a d-dimensional lattice with n size in total and L size in each direction. So the system Hamiltonian we use is a summation of local terms where each local terms is bounded by some constant and acting on spin on qubits within a certain distance of some center. So now we want to essentially apply the Lieb-Robinson bound to this local observable setting. I will first provide some intuition on how the Lieb-Robinson bound works. So the way this bound works is utilizing the fact that quantum information propagates at some finite speed v. What this means is in a Heisenberg picture on a 1D chain, for example, if we have a observable acting on this qubit in the center, then as time propagates, we create this light cone structure where only the qubits in the light cone will have will be impacted by the observable that was initially at this qubit. So all the qubits that are far from these light cone lines have exponentially small correlations with the initial observable. This is how we achieve an independence of system size for the error scaling, essentially. So applying this Lieb-Robinson bound, we get to our next result, which is essentially saying that as before the setup, here we have a local observable O and a local Hamiltonian H. We have a perturbed Hamiltonian H prime, and we show that their error bound scales with t to the d over 2 plus 1. Again, just a reminder, d is the dimension of the lattice space. So what this means is that stronger than the previous derived bound of t to the d plus 1 without the error cancellation case. Again, when gi is simply a constant delta. This is how, in order to use the Lieb-Robinson bound, there is some restriction as to the local errors, which is the reason we place the physical noise being bounded restriction on when we define the chi-deformed Gaussian. So here we need to assume that the noise is spread evenly across the system in order to have this result. Next, we can also extend our result to the fidelity decay setting. So the way we set up the fidelity is as following. We have some initial state, psi 0. We time evolve it under ideal Hamiltonian H, get to psi of t. And time evolve it against under perturbed Hamiltonian H prime, get to psi prime of t, take their inner product and norm squared. This is our metric for fidelity. And our result is as following. The fidelity is lower bounded by the exponential decay with factor of that's square root of number of qubits, which is, again, better than the previous bound where the exponent is linear in n. So interestingly, this is also independently experimentally observed by Adam Shao from Manuel Andre's group at Caltech, where they had a slightly different setting, but very similar to ours. And they were able to show this non-exponential fidelity decay experimentally as well on an Adam platform. Lastly, a simple numeric experiment to support the result. This is an 18-qubit system, time evolving under a Heisenberg Hamiltonian, where we have pairs of interactions. And we measure local observable y on the second qubit. And here, you can see the random error, which is the case with the cancellation, scales better than symmetric error case, which is the case without the error cancellation. So in summary, we showed that under this assumption that random noise, each qubit has a random or stochastic noise coming from independent sources, we're able to show improved scaling in error bounds because of the error cancellation properties. Specifically, we showed quadratic improvement in the general observable setting and extended results for system with local interactions and for fidelity decay. Some future directions to further tighten the bonds include thermalization. So when the system thermalizes, the state converges to some fixed point, which means the error would accordingly eventually converge to some very small value as well. Symmetry could, with symmetry, we can also more easily detect errors. And lastly, in many body localized system, the Lieb-Robinson bound actually isn't very tight because of it has a slower propagation of information. So for this specific case, we can also further tighten the bound. So that's the talk. Thank you so much for your attention.
Thank you for the talk. So here you showed these results for a very particular noise model, did I understand correctly? Like with local qubit noise and with these Gaussian distributions.
Yes, but the assumptions we place are pretty mild in general. You can still think of the noise model being uniform distribution or a Gaussian that's truncated at some point.
I see. Because my feeling is that these improvements due to error cancellation should happen for like much more generic noise models. And maybe I just misunderstood. Like, does your theorem actually work on much milder assumptions?
We use the assumption that is chi-deformed Gaussian, which we think encompass much of the natural distributions that can be used to model the system.
I see. So do you suspect that this result can be generalized to like other distributions, maybe not local distributions, non-Gaussian distributions?
Yeah, good question. So here our errors they don't have to be from individual qubits. It can be from individual sets of qubits. They can be correlated as long as the correlation is decaying exponentially or polynomially with large factors. Our results can also extend to the setting with a coherent error as well.
I see. Very interesting. Thank you very much.
Yeah, thanks for the talk. I'm wondering if you've thought about lower bounds at all, and in particular, I guess like based on the logic that you gave, like I might hope that the linear in T could potentially become like square root of T, in the sense that like the volume all contributes in this like stochastic way. Is that definitely ruled out, or?
That's a good point. I think it gets pretty complicated when you try to derive lower bounds in these settings. But it's definitely something to look into.
Thank you.
So if I understand the model, you start with a perturbed Hamiltonian H prime, then you evolve the system according to H prime for some time. Then you get another random HI and you do the same procedure and then you average. Is that correct?
So this H prime itself is made up of random variables.
It is set in the beginning, and it stays fixed along the coherent time evolution. Is that right?
The H prime?
Yeah.
Could you repeat that part?
So H prime does not change as you evolve the system in time. I mean, you fix it in the beginning, you evolve it for, I don't know, for 2 seconds, and then you repeat again with the new H prime that is drawn from this Gaussian distribution, and you do it again and again and again, and you get you set the average in the end, right?
H prime is fixed from the beginning.
So, but what makes it physical in that sense? I mean, why wouldn't the perturbation change in time as well?
Well, we think the H prime could be extended to the time-dependent case as well, but the analysis does get more complicated.
I see.
Yeah.
I have a very basic question. I'm not very familiar with these kind of settings. So in your work, like you assume that mean error source is like coherent errors, but like I think in many quantum computers, the mean error source will be like incoherent errors, like depolarizing or like amplitude damping or something like that. So I was wondering why you assume that the mean error source in your like analog simulator is coherent error.
So the key part of the proof was the fact that each individual error source has a zero mean, essentially, which give us the leading order term vanish. Let's see. So the main result goes back to the this part, where if you product together with odd numbers of i's, or with an odd number of k's, the expectation value goes to 0. This is from the assumption we place on the local error model. So this is kind of a restriction to have this leading order term vanish.
So you mean like you need to assume coherent errors to obtain such kind of relationship?
Yes.
Okay, thank you.
Thank you very much for this nice talk. And so let's thank our speaker again. Okay, so our next speaker is Nicholas Rupin, which is yours.
Thank you. Hello, everyone, and glad to be here. This is going to be a little bit of a break from TCS, or Theoretical Computer Science. My name is Nicholas Rubin. I work at Google Quantum AI on the algorithms team, usually focusing on compilation and design of physical simulation algorithms. I entered quantum information about 8 years ago now. And before that, I was a computational condensed matter physicist working on chemistry things. And so this talk today is actually going to be at the interface of these two topics. Now, this title sounds like something that might have been generated from Gemini or ChatGPT. It is indeed about how to apply quantum computers to the modeling of inertial confinement fusion. And this was actually a really surprising application of quantum computers that I'll talk about. And so the work has been actually in collaboration with many people, largely with a group from Sandia, QSimulate, and then special thanks to Dominic Berry, who's sitting in the back there, working at quite a lot of the compilations. And so I'll be representing the overall group. Okay, so just as sort of a preliminary before we get into the fusion modeling, one thing that we've done at Google is develop a small industry of analyzing constant factors in algorithms for physical simulation. Physical simulation, I probably don't need to introduce as a very valuable application of quantum computers. And so our goal is actually to understand precisely how long the best quantum algorithms are going to run for simulating important problems in condensed matter physics or specifically chemistry. And so you've probably seen us talk about academic problems like FMOCO. This is the active space of an enzyme that fixes nitrogen from the atmosphere. There's been a lot of hype about applying quantum computers to drug design. And specifically, we looked at something that actually has an open computational chemistry problem, which is P450 here, and then also things like battery cathodes. And so the way that these problems actually work is that we go and collaborate with a lot of chemists, and we figure out precisely what is the type of computational question that they need to ask to answer some particular problem. So, for example, in the P450 case, I hope all of you have avoided COVID, but if you did get COVID, you might have taken Paxlovid, which is an antiviral, and that is actually a drug cocktail, one of which is a P450 inhibitor. P450 is a drug that is an enzyme in your body that actually metabolizes a lot of xenobiotics, and so to make the antiviral more potent in your body, you actually inhibit it so it can stay in there longer. And so actually, this is a drug anti-target, and there's a particular simulation question related to what is the catalytic cycle here? Okay. So all of these models or all of these studies, we have some motivating computational chemistry question that actually boils down to asking questions about energy differences. And so what we do from a quantum algorithms perspective is try to understand precisely what would be the cost of simulating sampling from the eigenbasis of these systems. And so in chemistry, a lot of the work has been looking at second quantized simulations, which is a 4-mode fermionic Hamiltonian. If you saw Dominic Berry's talk earlier in the week, he showed over the years there's been substantial progress in bringing the cost of these down, but most of them work as follows. We are defined some Hamiltonian here related to the chemical system. This is knowledge that your computational chemistry friends have commonplace in their field. We then use a linear combination of unitary representations that allows us to block encode this Hamiltonian. From this block encoding, we can construct a walk operator and phase estimate that. The phase estimation, the number of queries to this walk operator are going to scale as a very important parameter, this lambda, which is effectively the LCU1 norm that allows you to block encode, namely put a Hamiltonian with a very large spectral width into a unitary. Okay, so this is the type of process that you might in TCS asymptotically discuss. You might end at this and say, okay, it's very easy to derive this thing. And what we want to do is go one step further and analyze the constant factors. And so a lot of the freedom and improvements that we have seen in the algorithms over the last 4 or 5 years have actually been leveraging the fact that we have quite a lot of freedom in the linear combination of unitary representation of this Hamiltonian. There's quite a lot of structure in this 4 tensor that represents the chemistry Hamiltonian, specifically because this is coming from a Coulomb interaction, a physical interaction that we know leads to a positive semi-definite matricization of this tensor and other things like, for example, its low rank. And so we actually compile the LCU for these using a particular form of the linear combination of unitary representation given the 4 tensor decomposition of the Coulomb integrals. These are just tensor network representations of this particular 4 tensor here. These all lead to global scalings that have fallen over time, effectively something starting like about 5 years ago that scales as n to the 4th, where n you can think of as maybe the number of a constant factor times the number of electrons in the system. This is the number of basis functions. And then to today, where we have some of the best scaling algorithms that are scaling cubically in the number of basis functions. And we can, after compiling everything, get leading order costs for simulating these systems within fault tolerance, all because we want to understand precisely how long these are going to take because of the overheads of implementing fault tolerance and performing quantum error correction on a real device. Some operations, of course, like Toffoli gates or T gates, are going to take substantially longer or have much, much larger space-time volume than Clifford's. Okay, so where do we get to fusion? So you might have concern that we know that generically simulating ground states is UMA hard. And so you might have concerns that this problem of using a quantum computer to simulate the ground state chemistry is maybe not the best place to look. A much more natural place to look is actually quantum dynamics. In some sense, this is the only thing that quantum computers do. They implement things in SU2 and SU4, right? And so this is sort of the natural language of a quantum computer. And there was actually a very surprising result from 2020 or 2023, just last year, from our group that showed that you can actually get a quadratic or a super quadratic speedup, a quartic speedup in some conditions for simulating the dynamics of electrons in first quantization over even the best classical mean field methods. So if you had some particular mean field method to simulate electron dynamics and you did the best that you possibly could, like time-dependent Hartree-Fock or time-dependent density functional theory, within first quantization representation, we could actually get a speedup over that. And so this was a very surprising result. And so what we did was then searched for applications of electron dynamics that effectively would enjoy this speed up, and we could go find an application that's motivating for this particular problem. Another thing that was actually interesting that came out of that work is that the speed up actually increases at finite temperature. And so this prompted us to look at in the warm dense matter regime. If you are a condensed matter physicist, you'll know that this is a pretty challenging area to simulate. For example, this phase diagram here, we have gases and liquids, and then all the way up here we have, fusion, the sun, and cores of white dwarf stars. And it turns out that indeed there is a problem in fusion that lives very nicely in this particular regime. So if you think of fusion, you think of hot things, right? And the physicist in me might think, well, if it's really hot, there's probably not a lot of quantum mechanics going on, and mean field methods would be particularly applicable, and they would capture most of the physics that you would need in terms of a modeling problem. But it turns out in the inertial confinement fusion setup, where they're actually fusing deuterium and tritium to produce a bunch of energy and an alpha particle, most of the time, this fuel is actually just sitting in the warm dense matter regime. And the goal of the group at Sandia is actually to model the hotspot dynamics of this particular process, the fusion of deuterium and tritium. You just get these hotspots that lead to more fusion as the fuel is traversing between 5 orders of magnitude between the lab conditions all the way up to something on the temperature of the sun. So this is a great target for simulation because it's very hard to make experimental conditions that satisfy that. It's hard to build something that is the temperature of the sun in the lab. And so primarily the focus of all of these studies is computational. Okay, so what exactly do they model? The thing that they want to understand about a material that or these deuterium-tritium mixtures at various temperatures and pressures is actually something called the stopping power. Now, this is the source term for a lot of the hydrodynamics equations for these hotspots that lead to modeling of these particular fusion processes. And stopping power is not actually a power, it's a force, it's a frictional force. If you remember from Physics 101, the force is derivative of the potential energy, right? And so here what we want to model is actually the drag of an alpha particle as it traverses a medium, namely this deuterium-tritium fuel soup effectively. So what you have as this setup is something that looks like this. These gray dots here are, I had a nice video, but it doesn't actually show up in PDF form. What you have is these gray dots, and these are deuterium and tritium. And here we can label one of these as an alpha particle. And you want to understand precisely how much this is slowing down as it traverses this medium. And this is a quantum dynamics problem. The way that they do this at Sandia is they start this on some trajectory, and it goes around this box, and it wraps around. And they actually translate this particle at constant velocity. It's not actually relativistic. It's about 3 or 4 AU. And so they just watch the system heat up. And the amount that heats up is the amount of work that's done on the system. You can also use Newton's third law and say, well, how much work the system is doing on the particle, or what is the energy loss of the particle? And that's the goal, namely trying to understand precisely how much energy is lost by the alpha particle to the medium, leading to heating, leading to more diffusion. Okay, so they want to extract stopping power, right? That's the derivative of some energy as a function of distance. So they have to have fairly long trajectories. They usually do this with a series of classical TD-DFT calculations and phenomenological models. Most of these calculations are on the order of hundreds of millions of CPU hours. And the interesting thing here is that there's actually not a lot of techniques between, for example, TD-DFT, which is a mean field method, all the way up to the exact simulation. So there's not a lot in between that you can do from a computational perspective. So this is a motivated problem that a group already spends quite a lot of time simulating, and we wanted to understand precisely if quantum computing can help with this particular setup. Okay, so what do we want to do? We want to understand the energy loss of a projectile as it traverses a medium, i.e. the work from drag, and the drag is induced by the electrons in the system on this charged particle. Remember, an alpha particle is a charged helium effectively. The kinetic energy of this, so we want to model the kinetic energy of this particle as it crosses a time horizon. And so this is exactly the type of diagram that we might expect. As a function of the displacement of this particle, so how much it's moved in our computational box, we want to look at the work or the change in the energy as a function of time, which is the slope. These spikes here are all actually physical processes of the alpha particle getting very, very close to one of the fuel atoms like deuterium or tritium, atoms. So we have a lot of choices actually when we design a quantum algorithm for this. We can do the same thing that we do classically. So for example, we can run the dynamics to a particular point in time and then perform phase estimation to estimate the energy while traversing the particle through the box at constant velocity. This is what would be exactly analogous to the classical case. What we can also do, and what we do in this work that saves quite a lot of resources, is actually promote the particle from a classical particle all the way to a quantum particle, and then treat the entire evolution in first quantization as a non-Born-Oppenheimer simulation. So effectively, we'll have a wave function for the electrons, or we'll have registers that represent the wave functions of the electrons in first quantization. These would be the X, Y, and Z components in each direction. And then also a set of registers for the projectile wave function. And then simulate the entire process unitarily, and then at the end of the simulation, measure the kinetic energy loss of just the particle on this projectile register. And that's sort of the setup that we're going to have. A lot of this work is actually guided by classical simulations, TDDFT calculations that tell us exactly the accuracies that we need to simulate to for a lot of these problems. And so here, this is sort of this interplay between taking ideas from asymptotic ideas and the simulation advantage and actually applying them to a physical setting where we can actually get a lot of constant factors in terms of the accuracy that we need from simulation and experiment. Okay, so what does it actually look like? Here's a slightly less cartoony version of this. First, we have our representation of our Hamiltonian in first quantization. Here's the Hamiltonian for the electrons. I've just sort of brushed that all under the rug. And then also we have our Hamiltonian now for the projectile, its kinetic energy, its interaction with all the particles, all the other particles, and all the other electrons in the system. And for the electrons, we actually want to prepare these in some thermal state, right? This is a finite temperature process. And what we've determined actually through some amount of classical TDDFT calculations is that the Mermin-Kosham initial wave function, which is effectively using the Fermi-Dirac distribution to occupy higher energy states, is a good initial guess for these systems. So we will sample from this particular trajectory, which we can actually prepare wave functions from in linear time, linear in the number of basis functions. And then the projectile, we're just going to represent as a very finite Gaussian distribution. There's some details here about how we actually select the width of this. If you're, for example, want to measure the kinetic energy just by sampling, you might expect that if this is very, very narrow, I don't have to sample very many times to actually look at the kinetic energy of the system. And so I don't have to do some fancier Heisenberg scaling method. I could just run my fault-tolerant algorithms for dynamics and then just measure on that register at the end. But it turns out that if you did that, the Fourier transform of a delta function in momentum space, of course, is a Dirac comb in position space. And so that would give this particular alpha particle a physical extent that's larger than the simulation box. We get around this actually by looking at the potential of the alpha particle on a particular grid spacing that we get from DFT simulations. And we can choose a finite width such that error is smaller than the resolution that we would need for this simulation. This leads to a result that we can use a Gaussian wave packet for the initial state of the projectile, the alpha particle, that has a variance of about 6 in the units of our problem. Of course, in first quantization, the number of basis functions, we get the number of qubits required to represent the number of basis function is logarithmic scaling. Effectively, you can take a register and then each of the computational basis states represents a basis function of your system. Okay, so I'm going to go a little bit quicker here. The next step is actually performing the unitary dynamics, and we explored 2 different strategies for this. One of which is actually using quantum signal processing to build the propagators and then time evolve after we've prepared an initial state. This is a fairly well-known result where we take the blocking coatings originally proposed in these papers for first quantization, augment them with the non-Born-Oppenheimer projectile, and then build the QSP circuits necessary for time evolution. Again, we expect this to be linear in time and linear in the lambda parameter for our blocking coding. Effectively, what we're doing is building polynomial approximations to cosine and sine and implementing that. This uses the improvement from Dominic and folks that gets the factor 2. I think there's a poster on it outside. The other methodology that we explore is actually a real space grid form and applying Trotter to this case. So there's this very nice paper from Guanghao Lo, Yuan Su, Yutong, and Min Tran about giving particular scaling or very tight bounds for how the difference of a particular Trotter formula or product formula and the exact unitary would scale in a fixed particle manifold for a lattice model Hamiltonian. And what we do in this setup is we actually imagine not simulating in momentum space, but position space on a grid, and then determine the constant factors here through numerical simulation. So we explored, various Suzuki expansions, and then also made our own bespoke 8th order product formula, which ended up being a pretty efficient one here. These simulations usually go up to about 125 qubits at low filling, and then we extrapolate these to higher filling settings. Another example of this, of an optimization, especially something that we worked on that reduces the cost quite a lot, is that if you want to implement the kinetic or the Coulomb interaction on a grid, what you need to do coherently, what you need to do is actually compute 1 over square root of r, or 1 over the distance, and that requires you to actually compute this 1 over square root r distance. And right now, or before this work, the best methods were using about 10,000 Toffleys, employing a Newton-Raphson type protocol. So Newton-Raphson, you can reduce this computation to just additions and multiplications coherently, but it takes many iterations of that. That's actually a very common trick numerically to do. And we improved that here through a combination of function approximation QROM and a single step of Newton-Raphson. In the last couple of minutes here, I'm going to give some of the results. The last step is actually calculating the kinetic energy loss. Remember, we want to understand precisely how much energy our projectile has lost to the medium. In this particular setup, there's no relativistic losses. And so the main loss is indeed effectively frictional loss, the stopping power coefficient. And we know that in the accuracy regime we have here, we actually need very few samples to actually get a good estimate. And this is again coming from the fact that the alpha particle is effectively classical. We're just using a non-Born-Oppenheimer description to make our life easier in the quantum algorithm setting. And we can use classical TD-DFT calculations to get an idea of how much we need to sample for a fixed amount of accuracy. We also compared that to a very good scaling mean estimation algorithm from Robin Cathari and Ryan O'Donnell that came out a couple of years ago. This enjoys Heisenberg scaling, which is effectively employing a type of Grover type speedup. There, the constant factors are much, much higher in the sense that though it does have lower asymptotic scaling, of course, at the regimes over here on the right, where we actually are in terms of the errors that we need to we're able to tolerate on the estimate of the kinetic energy, just straightforward sampling ends up being the way to go. And so this is sort of a long story in terms of using our insight of the requirements for accuracy and comparison to classical methods with classical computers to determine which are the best quantum algorithms to employ in which particular setting. Okay, so at the end of the day, we are able to compile the algorithms, just like we did in the second quantized chemistry case for time dynamics, using quantum signal processing to synthesize the propagator, and then also applying our 8th order product formula. And indeed, actually, it turned out that the product formulas are slightly cheaper here. The reason that we were doing those numerical estimates of the constant factors is because this is a much tighter bound than commutator bounds that you, or the much tighter estimate of the performance of Trotter over something like commutator bounds. The number of qubits here is actually higher in the product formula case. Most people actually see this slide and ask why that is the case. And that's because there is a QROM here that we're using for function approximation that helps out with the efficiency. And so to put this all into context, I'm about to finish up here. let's take the chemistry examples that the field, I think, would consider flagship, that P450 case and the FIMOCO case. There we needed about 3 times 10 to the 10 Toffoli gates, here 7 times 10 to the 9. And this is the first time that we're actually looking at a quantum dynamics problem at this scale, or what I would call an industry scale, or a scale that is relevant to another large scientific project. And we're really only about 3 orders of magnitude off of the best classical method or the best simulation methods for chemistry that have been optimized over the last 5 or 8 years. And so I think there's a lot of hope for expanding or improving these methods such that these costs really come down greatly. I'll just very quickly say that a lot of the compilations are done in our group using a tool called Qualtran. What we do is a lot of the algorithms in first quantization, second quantization are written down in papers in sort of either a combo of circuits and English prose. We've systematized a lot of that, and we use this particular tool, which is a graph-based representation of the algorithm. And it also lets us generate circuits very easily and check things. And then we can do analysis such as look at the highest complexity subroutines. For example, this one is actually just the cost of swapping electrons into the active register for first quantized simulation. And so this actually ends up being the highest cost. The second highest costs are things like nested boxes, state preparation, and things like that. Okay, so just as sort of a bunch of takeaways, this is the first, at least to my knowledge, really industrial scale dynamics problem that has been cost out and that we're trying to understand all the constant factors for. A lot of this work is about the interplay of how to develop a quantum or take ideas from quantum algorithms development and then sort of apply them in a clever way to a particular simulation problem given the accuracy requirements for that problem. For example, taking advantage of what type of grid resolution we need, how we represent the projectile, what type of temperature, for example. This is the first non-Born-Oppenheimer blocking codings for first quantization. They were articulated in Yuan's paper back in 2021, but I don't think the actual blocking codings were provided. Then there were a couple of other tricks that Dominic introduced that lets you get very, very efficient computations of Coulomb interactions in this particular representation. With that, I'm happy to take questions. Thank you.
Hi, yeah, thanks for the talk. These plots you had on the last or second to last slide on the left 2 plots, like, could you say again what the, sorry, before, yeah, those. Is this data that was generated classically, like the kind of data you'd like to generate on the quantum computer, or?
Yeah, so this green curve actually comes from a stopping power calculation done by our Sandia colleagues for the inertial confinement fusion experiment they have at Lawrence Livermore. And what we were doing there is taking the output of the Mermin-Cohen-Sham calculation that they're doing and modeling the calculation of the stopping power as a from sampling, effectively using the output of the TDGFT calculation. That gives us an idea of how many samples that we need to actually take. So here's stopping power, and each of these are run with a number of samples, and this is like the accuracy that we're getting for each of these. And so this sort of tells us how many times we need to, if we were to run the quantum computer, how many times we would actually need to sample. This is just an empirical estimate of how many samples we need to get this type of precision, which is already extremely high for this problem.
I see. So the number of samples is incorporated into the overall Toffoli count?
That's correct, yeah.
But would then like you take those samples and you generate 1 point on the left? Is that for all of the points on the left at once?
No, it would just be 1 point. And so, we're interested in this at different, just like in chemistry, you're interested in the energy calculation at different configurations of the molecular setup, and like all of the numbers are for one particular configuration. For example, this would be the same sort of setup. This would be for 1 point, and we're interested in different velocities at different temperatures, for example. And so we have to run this over and over again.
Right. So I guess I'm wondering if you have a sense of, for Sandia, like how many of these points do you think they would need? Is it like 10 or is it like 1,000?
So this is another thing that actually makes this problem very fun. Right now, the only physical data set that we have on stopping power for deuterium, tritium, simulation has like 4 data points in it. And they have these great heat diagrams that they like think the partition function is for this, and they try to like map out the phase diagram, but it's like a complete guess. And so they're like adding a handful of data points to that, surface would be extremely useful for them. So I think just a handful of these calculations would be very useful. And also, even at these very, very small scales, this would let them sort of benchmark a lot of the TDDFT calculations that they're doing. Those have uncontrolled error. So they really want to know, given a high accuracy simulation, what are they incurring in terms of error?
Okay, yeah, thanks. That's very helpful.
Thanks for the nice talk. So my question would be, within this simulation, can you apply it to, say, phase transitions, like superconducting phase transitions, second order, like liquid, gas, fluid type dynamics?
Like in a non-Born Oppenheimer setup?
Exactly. Well, you need it there.
Yeah.
And
yeah.
the part of this question, can you approximate high moments, high correlation functions?
So for the superconducting example, I actually am not sure how to do this in first quantization, given as an input to the first quantization simulations, you need to fix the number of particles, right? And if you're to ab initio simulate superconductivity, you want to see some condensation in Fock space, right? And Fock space doesn't have a fixed particle number. And so it doesn't make sense to me on how to do that. But I think there's other ways that you could simulate that transition, for example, looking at conductance and things like that.
No, but I mean the approach. So basically you have this creation annihilation operators. You just build another Hamiltonian with another tensor in your like prefactors.
And in second quantization, yes, of course, this is easy to do. In first quantization, no, I don't think you can do it that way.
Okay. Then the part for this particular simulation, can you approximate the second order, third order correlation functions for this particular dynamics?
Yes, the cost likely goes up as the norm of those, the norm of the operators defining those correlation functions. So going back to the superconductivity thing, of course, you would then need to measure like the 4-mode correlation function, for fermionic mode correlation function, and the norm of that is going to be higher.
Okay.
So thank you very much for this talk. Let's thank our speaker again.
It should be fine.
So let's start the last session of today. And the first talk is by Alexander Belov, who tell us about how to tame quantum time complexity.
Okay, thank you, Alex. So yes, so this talk will be really about time complexity. And first, I'll give some historic introduction. So like this line of research, like in general, I'm not talking about just my work. It started maybe with this problem. It's a well-known problem. It's not-end tree. So we have such a tree, so it can be like really long. And at the end, at the leaves, you have variables. And we want to evaluate the value of this expression. Like maybe what's the query complexity, what's the time complexity. Okay, and so naive solution would be to use Grover's algorithm for not-end and just compose them together. So to use solution for a subroutine as input to a next subroutine, which is one level up. Okay, so it works. So like if you have one not-end, it somewhat works if you have two not-ends nested together. Okay, but the problem starts that Grover is not exact, and you have to reduce error, so to make all of this work, so that the error just doesn't blow up everything. And so this introduces log factors, and like the more layers you have, like the more power of your log factor is. So if you have 17 layers, you have essentially to pay log to the power of 17. Okay, and so this essentially kills all the advantage you get with Grover. Okay, so the solution to this problem, I am skipping quite a lot here. Okay, but a better solution, better algorithm was obtained for query complexity. So this is, as I said, a long line of work, and mostly done by Reichardt, but also some other authors that I don't list here. Sorry about that, if you are one of those. Okay, and the idea is to use span programs, or which is essentially the same thing, dual adversary bound. Okay, so and the idea is as follows: and you start with your algorithm, and you can convert your algorithm, which is bounded error query algorithm, can convert it into a span program, or if you wish, you can design span program from scratch. Okay, so then you compose span programs together, and then at the end you take a span program and you convert it back into a query algorithm. Okay, so essentially it's, somehow there is a real world and there is ideal world. So ideal world are the span programs, okay, which are composed without error, so exactness, and you can somewhat transfer in both directions. Yeah, so what's so this is really nice, and this gives an optimal algorithm for not-end. Okay, but the problem with okay, one small problem, also maybe not a problem, maybe a feature, that's how you think about it, it's the change of the model. So span programs, they look completely different than query algorithms. So if you are used to quantum algorithms, then just getting to use span programs can be really complicated. Okay, so recently, so it was a work by myself and Yoko. So we obtained the notion of quantum Las Vegas query complexity, so which has the same benefits. So that's the first point, the same benefits with the span programs. Okay, and it uses the same model. So it uses, it's also a quantum algorithm. What changes is how you define complexity. So let me go to the next slide. So one big disclaimer. So here, when I'm drawing two lines, two parallel lines, they correspond to direct sum, not to the tensor product as usual. And I also use this arrow just to indicate this. So everywhere, these are direct sums. Okay, and so for every quantum query algorithm, you can rewrite in this way. Okay, I assume that you can apply your input oracle conditionally in a controlled way. So there is some part of the state that is not processed by the oracle, and there is some part of the state that is processed by the oracle. So the standard definition is just the number of times you execute the input oracle. So in this case, it would be 3. Okay, so you define Las Vegas complexity. So you define query state as a direct sum of all these states you give to your input oracle, and you define Las Vegas quantum query complexity as the norm of this state. Okay, so the sum, norm squared, sorry. So the sum of norm squared of all the things you give to the input oracle. And in this way, you can give like a tiny part of your state to the oracle. So for instance, you can have a controlled operation, then you decide whether you need oracle or not. So you're only paying for the norm that you actually do process. So in a way, you can see this is a probability that you like the sum of probabilities of expectation, the expected number of executions of the oracle. Okay, and so it's nice, and it behaves like randomized Las-Vegas complex. So if you're used to randomized Las-Vegas complexity, one of nice features is that it's very nice composition results. So this is just one example. So I have an algorithm which have a bunch of subroutines, like a big oracle that everyone calls, and I'm interested in the number of queries. So this is the query complexity of the composed algorithm. So this is the number of queries given directly from I to the input oracle, and this is the sum of all query complexities of individual subroutines on the state that is given to them by I. And so one feature of Las-Vegas query complexity is that complexity depends on the input. So for different inputs, you can have different complexity. Okay, so this is really easy to prove for Las-Vegas complexity, but it's hard to attain using standard techniques because you don't know what the state is, so you have to run the worst number of times. But whereas in this case, it's automatically computed for you. Okay, and we call this thing thriftiness. And so the goal of our research is, can we get the same benefits like exactness and thriftiness for time complexity? And another result problem that current algorithms do not utilize Las-Vegas complexity really nicely. For instance, if you use Grover, the Grover acts with query on all the state all the time, and the result is that it's overcooks the state, so we know very well. And so that's not nice. So we need slightly different types of algorithms. So we define this notion of transducers. Okay, so this is a purely linear algebra at this moment, and it's a theorem that is quite easy to prove. So if you have S is a unitary, we should call it transducer. And so it acts in a direct sum of two Hilbert spaces, H and L. And then you can prove, if S is a unitary, then for every Xi that comes in, there exists unique tau and essentially unique V, which we call a transducer, such that S transduces, as how it's depicted here, it transduces Xi plus V into tau plus V. And moreover, this mapping from Xi to tau is unitary, and so we denote it as this kind of restriction, transduction action of S on the space H. Okay, and so how we can use it? So this is like this our transducer, and instead of thinking about this as a unitary, we think about it as its transduction action on this space. So this is somehow a private space of the transducer. We never access it. What's happening? Oh, good. So and so the transaction complexity is defined as the norm squared of the transducer, of the catalyst. You can also call it catalytic complexity, and so it's very similar to witness size for span programs. Okay, and there exists an algorithm that executes every transducer as a black box, the number of times which is equal to the transaction complexity, and approximately transforms Xi into tau. So this makes sense, all this stuff. So how the algorithm works, very briefly I will explain. So this is a transformation I want to perform. I want to perform Xi into tau. This is a transformation I get just by the definition of transducer. So Xi plus V into tau plus V. Okay, and this is what we actually transform. Xi plus V divided by square root of K, where K is a large integer. And so if K is a large integer, this part is small. And so this is where approximation comes from. So you can neglect it and you get some small error. So it's pretty standard thing. Okay, and so that's the main idea how the algorithm works. We just execute Sk times, where K is this thing. We have this V divided by square root of K. It just sits here as a pedal tone all the time. Okay, and then we just transform this Xi into tau piece by piece. So we break it into K copies, where K copies are additive. Okay, and then we process each copy by itself. So it's very standard algorithm. Very easy to see why it works. Okay, and so let me first very briefly talk about queries. So I draw this picture of a query algorithm which is like a canonical form. So you can also get a canonical form of a transducer, which can make queries. It turns out that without loss of generality, you can assume that there is only one query, which is applied at the very beginning, and it's a part of the catalyst that is processed by the oracle. So it's very simple standard form. Okay, and so this S circ doesn't use input oracle at all. Okay, and so why can we do this? So this is the query algorithm in general, which we saw. You can also think this as a transducer or as an algorithm. And so how can we get a transducer out of it? So we just wait and calculate what the query is. Transducer doesn't do that, it just guesses what the query state is altogether. So it's the catalyst. And then we perform our algorithm as before, but instead of making a query, we substitute what we query to the already processed query. Yeah, so instead of this picture, we have this picture. So we have just one query, as in the very beginning, as promised. Okay, and the size of the transducer is Las Vegas complexity. So it's just the query state. It's the direct sum of all the things given to the input oracle. Yeah, so that's how we get this canonical form, just by guessing and then substituting, essentially checking whether we guessed correctly. Okay, you can see that this is equal to this. So this state is equal to this state. Okay, and so that's how we convert Las Vegas query complexity to usual query complexity. We just use this construction, it's transducer, and we execute the algorithm from before. Yeah, so in general, there are three complexity measures of a transducer. So this part is a bit not so nice about them. So we have to deal with three different things, but okay. So the one thing is time complexity, which I've been neglecting so far. It's okay, so this is just a unitary, a usual circuit. So it's the number of gates, or the time you have to spend to actually implement this unitary. So if you have to do that. Okay, and another two things, so this is just time complexity. Another two things are purely mathematical, so it doesn't depend on your model. So one is transaction complexity, which is already defined is the squared norm of the catalyst. Okay, in this case, catalyst is broken into two parts. So one is not processed by the query, by the input oracle, and another one is processed by the input oracle. Okay, and so this is the same definition as previous. We just have two parts now. Okay, and the query state is the query state which is given to the input oracle. So query complexity, it's Las Vegas query complexity is the norm of the query state, norm squared of the query state. It's just this thing, norm squared. And you can, so the question is, why do you call it a query complexity? It turns out there is a refined algorithm which is slightly more complicated than the one I showed you previously, but not not too complicated. So it executes this part, this unitary, which is oracle-less, a number of times, which is transaction complexity, and it executes the input oracle the number of times, which is query complexity. So the number of queries is indeed the query complexity, and it, as before, it approximately transformed psi into tau. I don't have this on slides, but it turns out that it also works if you have multiple input oracles with different complexities. Then you execute each input oracle given the number of times which is given by the norm squared of the query state. Okay, so it's all in the paper. Okay, and another thing about this canonical form, that it's really simple. What you can do, so just to remove this thing, like the part of the state which is not processed by the oracle. So let me go back a number of slides to understand why. Because going back to this slide, you see that so without loss of generality, if we're only interested in query complexity, this catalyst is the query state. So all the catalyst is processed by the oracle. So if you're interested in query complexity, then you can just remove this thing. Then it's kind of easy optimization problem. We want to find the best catalyst so that we, so it's stays the same under application of unitary and transformed psi into tau for the selected pairs of psi and tau we want to transform. So it would be a state conversion problem in technical terms. Yeah, and if you do this, it turns out that the adversary bound. Yeah, right, and you get it like really fast. Okay, so let me now go to time complexity. Time complexity is actually the main selling point of our work, besides the definition of transducer. So we've been talking about query complexity. For time complexity, you can do a similar thing. So now imagine you have a program. Okay, so now I'm interested in the number of gates. So each GI is an elementary operation, a gate. Okay, and what I can do, just guess all the history state of the algorithm as a catalyst, and then just do the same thing as before. So essentially, so I perform all this GI in parallel. So I'm performing this operation, so direct sum of GIs or GTs. And it turns out, okay, so if I shift everything nicely, so this state preserved, I get in psi and I get out T. So it's like a history state that is shifted by one position. Okay, and this can be done efficiently, assuming quantum random access gate, which is a powerful quantum random access memory where you have quantum random access to quantum memory. Okay, and so what happens? Transaction complexity becomes time complexity, because okay, the size of the catalyst in this case is the number of elementary operations. So time complexity, so assuming this powerful gate is order of 1, okay, and the query state becomes query state. So I didn't draw it here, but you can combine the both things. So you can have queries which are processed and also have this time complexity. Okay, so essentially substitute transaction complexity becomes time complexity. So again, one point that you can also do things without assuming the quantum random access gate. You get some interesting results, but they are not so nice, I would say so. And I also don't have time to talk about them here. Okay, so then you can use, like, say, composition as before. So the same picture as before, which we had for in-query settings. And it's very similar. So now, but now instead of programs, I have transducers, which I compose. So it's not obvious how you compose transducers, but you can do this. It's not too complicated. And so it's not just where I have exactly the same model. I have to prove something also, but and design how I do this. But it's doable. So for query complexity, I have exactly the same expression as before, and a similar expression for transaction complexity. So the time complexity is just additive. So this time complexity thing is a bit weird, but if this is order of 1, this is order of 1, this is also order of 1. So I can essentially ignore it. Yeah, so remembering that transaction complexity is time complexity, so I get composition results which attain thriftiness in the same way as in query complexity. Okay, so another thing is, which is like a different thing altogether, is that quantum works turns out to give exact transducers. So one thing is electric quantum works. So quantum works is a really broad subject. Okay, but if you concentrate on electric quantum works, which is a powerful version of a quantum work that encapsulates many algorithms, including learning graphs and other stuff, then they are transducers, and they are exact transducers in the sense that they perform exact transformation without any error. And the analysis is extremely simple. And so this is a new paper, which I use this opportunity to advertise. So it's not in this paper, which I'm presenting, but it's a new result, that there is this exponential separation by a quantum work by Charles, Cliff, Diotter, Farhi, Gutmann, and Spielman, where they achieve exponential separation between randomized algorithm and quantum algorithm using quantum work on this graph. But their analysis was suboptimal and very complicated. Using transducers, the proof is optimal, so we can prove linear hitting time, and it's half a page of a proof. So it's extremely simple. So kind of also shows that you can do it in different ways. So my last Quantinuum slide is about purifiers. So purifier is again a different thing. So this is for results is majority voting. So that's how you reduce errors. So when I start talking about not entries, so I said that you reduce errors using majority voting. Okay, and so this is a formulation that there is a quantum procedure that gets as an oracle a bounded error unity. So bounded error unity means it's a program that evaluates your function's bounded error. So transducer, so purifier treats it as an input oracle. So we can reduce the error all the way down to epsilon in query complexity, which is logarithmic in 1 over epsilon. Okay, and time complexity is also logarithmic in 1 over epsilon. So using transducers and essential quantum works, you can get a purifier, which is a transducer that does the same thing. You can reduce the error to epsilon. The difference is that query complexity is order of 1. So it doesn't depend on the error you want. So it's still constant. The constant depends on the error you start with, so which is usually 1/3. Yeah, and time complexity, this is a bit slippery business. And so if we assume, again, powerful RAM model, we can also do it in constant time. So constant number of random access operations, essentially. Okay, and this way we obtain exactness. So I showed you how to get thriftiness on 2 slides ago. And now this is how we get exactness just by composing with these purifiers. Okay, and let me just summarize. So we define transducers. Okay, so it uses the same model. It's a quantum algorithm. So it's extends the definition of computation. So a different way how you can compute stuff just using where you guess a part of your state and just you have to, and this guess can be like really huge, but you have to ensure that it doesn't change during your computation, which is like non-trivial thing. Okay, and it has the same benefits as span programs for query complexity, but it also includes transduction complexity, which in parentheses means time complexity. So it can incorporate quantum works really nicely, as we saw. And so the open problems are applications. Whenever you have a complicated algorithm where you compose a lot of stuff, you can say, and assuming the QRAG model, we can use it as a black box. So if you next time want to do something like this, I would be really happy if you would just consider possibility of using this machinery. So maybe you can shave some work factors with this, or maybe attain a better improvements. Okay, and so also it's very interesting. So for QRAG, you use it as a black box. For like without QRAG, you have to work more, but it's on the other hand, it might be more interesting. So I think it's kind of interesting research directions, how much we can do it, like just using the standard 1 and 2 qubit gates. Okay, so and other ways to construct transducers. So we see quantum works and how we can convert any program into a transducer. Maybe there are some other interesting ways how you can get quantum speedups using transducers, which are out there. Okay, so that's it. So thank you very much.
Do you have questions? I have one actually. Can you go back to slide 14?
14.
Yeah.
Sorry, that's way too much. Yes.
One thing I don't understand, like this site 2 ball, like it depends on the oracle as well, right?
It depends on psi.
And in the oracle as well, because it could be.
Yes.
So then, but then isn't it a problem that in the bottom part you're guessing site 2 that depends on the oracle, or it's fine?
It's fine because okay, I don't really understand what you want to query. So one thing, it depends on the particular oracle that is here, but it's all the same oracles that we execute. So all these 3 oracles are the same. Okay, and so it depends on this initial state and the oracle. If you fix them, that everything is fixed. Okay, and so the algorithm just guesses it. Yeah, so it doesn't mean that it depends like on this output of the oracle. Well, maybe that would be the right question. So it depends on this execution, but we guess it. So sometimes the time disappears in this case. So we somehow get some parts of the state from mid-air, which we, otherwise we would have to wait for. Get access to.
Other questions?
Thanks for the nice talk. So my question is about the role of the catalyst. It's not exactly clear to me. Like, because you said that the transformation from Xi to Tau is always unitary.
Yes.
So why do we need to carry the catalyst in the algorithm? Can't it just be encoded in the unitary in some way?
Oh,
Like-
yeah. So that's a unitary, but the question is how hard it is to implement this unitary. So it can be that, okay, I think this would be the right side. So this unitary could be like really, so this unitary we usually define, and that's what we care about. Yeah, but it might be hard to implement. But this unitary might be very fast to implement. Yeah, and so that's how we implement it. So you can also think about this as a idea like a quantum walk, where you have one iteration of a quantum walk, which is actually easy to implement. It's just product of two reflections, which is each of them is easy. But if you run it for quite some time, you get a really non-trivial, non-local transformation. So the question is, so why we care is that this might be much easier to implement than this one.
Thanks.
Let's switch to the second talk of the session. So we have Minky Han on the quantum complexity for discrete logarithms and integer factorization.
Thank you for the introduction. I will today give a merged version of two lizard, partly joined with Aramun and Takashi Yamakawa. And yeah, I will talk about the generic quantum complexity about discrete logarithm and integer factorization, but it's a little complicated. So I mainly focus on the discrete logarithm and probably on about the first paper. Okay, as I said, this talk is about the limitation of quantum generic algorithms, but yeah, probably it's better to start with just a limitation about generic algorithm. Yeah, it's a kind of black box approach to the showing the lower bound. So in this model, we consider the generic algorithms where and we want to study some ideal functionality of a hash function or group structure. So we just assume that ideal functionality are given as an oracle, and algorithm only access them as a black box way or in a generic way. In this way, we can identify the kind of best possible hardness or best possible security of the hash function, some problem in group structure, and so on. So, for example, yeah, we already have so many lizards in this kind of model. The first one is, for example, for the function inversion, we are given a hash function. Then if we access them in a black box way, to find a preimage of some function, we require, we need to query every domain, every input in the domain. And for the discrete logarithm, which we care, it turns out to require square root of the size of the group for the secret group. And yeah, this is a well-known result. And heuristically, we believe that our best implementation of hash function looks like random oracle or idealized hash function. So yeah, it actually gives some evidence on the security. And it applies to the generic group, group structure as well for the elliptic curves. So limitation of quantum generic group generic algorithms are pretty much the same. Yeah, we consider the generic quantum algorithms, which don't care about the specific implementation of the hash function, group structure, and so on, and only allow the black box quantum access to the oracle. This probably identify the best possible post-quantum or quantum hardness of some relevant problems. And we already know many results about the function oracles or random oracles. For example, for the function inversion, global search obtain a quadratic speedup, which turns out to be optimal in the quantum random oracle model. And we already show the tight bound for the quantum collision finding. And we even know about the tight bound for the Simon's problem, which matches to the Simon's algorithm. So, but in this talk, we are talking about, not about the function oracle, we are talking about the group oracle and the discrete logarithm problem. This is everybody probably know the problem. We are given a secret group and generator and the problem instance due to the X and try to find X. In the classical setting, there is a so-called generic group model, which is a black box group. And in this model, we already know that the discrete logarithm requires a square root of the complexity to solve the discrete logarithm. But in the quantum case, Shor's comes in and everything's are broken. Yeah, its learning time is a polylog. And if we only count the number of a group operation, it's just a logarithm G. We will see it later more explicitly. And our results is kind of this. If we consider the generic quantum discrete algorithm, then Shor's algorithm is kind of optimal. That's it. We will talk about some recent progress later. So let's briefly talk about the implication. Yeah, there are some estimation about the Shor's algorithm, especially for the elliptic curve discrete logarithm. And it says that it probably requires a one day assuming many physical assumptions. So our result roughly says that, okay, for breaking discrete logarithm much faster, probably it's impossible unless very new algorithm appears. So we have some confidence about our security estimation for the pre-quantum cryptography. So unless we have a super large quantum computer, it's okay to use the discrete logarithm. Yeah, this kind of implications are much better when I upload the paper. But the problem is Legev give a efficient quantum factoring algorithm, which improved the Shor's algorithm. But I said the Shor's algorithm is optimal. It's just 1 month later of my paper, so I need to revise it. Yeah, I changed a lot of part of the paper because of this. Anyway, yeah, probably it's nice to see the brand new idea of Legev's algorithm. It's not on my contribution, but it's very simple. Yeah, Legev give a better factoring algorithm. And the brand new idea is just this kind of thing. 2 times 3 is equal to 6. It's easy. In the generic group model, we don't care about the group elements. I mean, every group operations are pretty much the same. But actually, if we are considering the circuit complexity, it's much easier than the other. So Legev used this kind of thing many times to obtain a better complexity. But in a sense, Legev algorithm also only use the group operation, ring operation. So our result kind of applied to their result. So their number of group operation obey our low bound, but it happened to obtain a better complexity. So it's a kind of orthogonal. And if we only consider the elliptic curve discrete logarithm problem, then there is no such this kind of easy group operation. So there is no Legev variant. So it's okay. Anyway, yeah, this is comparison between Legev's and our result. So how to obtain our result? Yeah, we give the very brief idea about the proof. But before then, we need to introduce quantum generic group model. And before then, we need to introduce generic group model again. It's just a black box group model. We only access the group elements in a black box way. So given 2 group elements, we can submit it to the group oracle and obtain a group operation like G to the I plus J or G to the I minus J. And we can check 2 group elements are equal or not by submitting them to the equality oracle. If we need to consider their quantum counterparts, then it probably works like this in the computational basis. But actual model should be much more complicated because there are many group elements and we probably can do the group operation in a superposition for the other elements. So, but yeah, I don't care about it. We maybe, it's okay to think about this one in this talk. So yeah, just for example, let's think about Shor's algorithm in the generic group model. We apply quantum Fourier transformation and some group operation and inverse quantum Fourier. Then it's all group elements and we care about it. But yeah, there are some other things which we don't care. So it's what we care, and yeah, we only care about this one. And to compute this one, we need to apply many group operation. And it turns out the logarithm number suffice because of this kind of binary representation. That's it. So Shor's algorithm can be described in a quantum generic group model. So how can you prove that this is optimal? Actually, the proof is also very simple. We just simulate any quantum generic group algorithm in just a classical generic group model. And then after simulating the quantum algorithm in a classical generic group model, we just apply the classical lower bound. One caveat is if we simulate the quantum algorithm in the classical generic group model, it can operate quantum over unbounded time as long as every group operations are classical. And yeah, usually that kind of classical simulation incurs exponential blowup. So let's say it's true in this case, then Q-query group operation algorithm can be simulated by exponential number of classical group operation. And this should obey this lower bound. By taking logarithm, we have the result. That's it. It's quite simple. And Okay, the classical simulation goes like this. Yeah, it's a kind of variant of a light cone argument. You can, yeah, in the initial stage, algorithm only have a identity group generator and the problem instance. After applying one group operation, it only can see the identity gy and g square, gy, y square, yeah. And everything can be expressed by the g to the a, y to the b, where a and b is small, like 1 or 2 or 0, -1. And this argument can be extended to every query. So after Q query, we only need to see this kind of small number of group operation, which is just an exponential number. So classical simulation just prepare this kind of elements using the exponential number of group operation, then simulate the overall quantum state of the quantum generic group algorithm. That's it. This is our proof. Yeah, we have some other, other lizard, but the proof lines goes very similarly. And as I mentioned, there are two proof. We have two paper. The second proof goes somewhat different way. Let's say algorithm by Alice and group oracle by Bob. And yeah, Bob prepare the problem instance. And Alice learns the algorithm. And whenever it needs a quantum group operation, it asks the group operation to Bob, and Bob do the group operation and send the kind of compressed result to Alice. In some setting, it only requires a constant number of qubits. But after learning the algorithm, Alice eventually learned the X out of G elements. It means Bob eventually send X to Alice, and it requires a logarithm number of qubits from Bob to Alice. It's a very standard argument, but yeah, it's a known result. And every group operation requires constant qubits, so it means Alice Bob need to, Alice need to make a logarithmic number of quantum group operation. This is the idea of the second proof. That's it. I believe it's both of them quite simple. Okay, let's talk about mode result. Actually, Shor's algorithm can be a little speed up at the cost of some classical pre-processing, pre-computation. Like, as I said, the G to the A, Y to the B requires a binary representation, but we can prepare we can use the base K representation and prepare somewhat more elements. Then quantum operation can be reduced something like this, log G over log K. And yeah, in summary, yeah, at the cost of many classical group operation, we can reduce the quantum group operation like this. And we also show that this is optimal. So yeah, we have this result in the first paper. And in the second paper, we actually consider much more different problems. Like we also consider the quantum generic ring model and talk about something about the order finding problem, which is the most important problem of Shor's algorithm for factoring. We actually have something about Legev's algorithm, but it's too complicated, so I don't want to say it explicitly. And we also proved the quantum multiple discrete logarithm problem, which means problem instance is not single one, but many things are given. And we proved the type bound, which matches to our new algorithm in the first paper. And we also recover almost all generic group hardness, for the generic problem in the classical setting, and say something about the index calculus as well. Yeah. In summary, let's come back to the generic group, quantum generic group model. We show that Shor's algorithm is optimal for the discrete log, which means any quantum generic group algorithm requires a logarithm number of quantum group operation. And yeah, if we allow the classical computation, it can be speed up, but we show that the tight bound. And actually, we say something about the quantum random access memory as well. And if there is a no quantum random access memory, then this bound is optimal regardless of classical pre-computation. Yeah, we show something about the depth or more hybrid algorithm, not just a classical quantum. We say something about classical quantum, but yeah, it's pretty much the same. Yeah, that's it. And yeah, I'm the best. Yeah, there's some open problem. One is our low bound is something like so multiple constant is not optimal, like 1/2. But Shor's algorithm, actually variant of Shor's algorithm can be done only using the logarithmic number of group operation. And I'm working on this with Morgi and Yokjun. And I think in the quantum setting, black box group models are not that studied well. So I'm really curious about can we do something similar for the other problem, like a generic group action discrete logarithm problem or non-abelian Higgs group problem? And yeah, I'm really curious about, yeah, if we can say anything about Legev's variant, but yeah, it seems very tough. Thank you. That's it.
Questions? I have one question. So one thing I don't understand, because as far as I remember, Regev's algorithm, the complexity is the same. It's just that they have a shallow circuit for the quantum part. So the number of queries that you need to the oracle, like to this generic oracle, the group model, it will be the same, no?
Yes.
So then, what's the question then?
Oh yeah, I want to consider some modified model, something like Legev. Small group operation can be done much faster than the other group operation. More fine-grained model, what I want.
Any more question?
Yeah, I was wondering if you could go back to the slide that's more results on the first paper. Yeah.
Oh, yeah.
So you said that this is the best we can hope for. I was wondering in what way?
In what way?
Yeah, like is it just like the like quantum group operations, or is it like for example, could you do you know that you cannot improve on like the QRAM usage on the second row?
Oh.
No, the top
one. You mean if there is no QRAM, can we do better?
For example, could you maintain like the group operations for the quantum and classical, but use like less than k-1 qubits or something?
Oh, actually not. Yeah, I very quickly said, but yeah, we showed that without large QRAM, this is optimal.
Okay, thank you.
Thank you for the question.
If you don't have any more questions, let's thank Minky again. I think it's yours. just Pedro, which one is yours? This one? Oh, this one. Yeah, we have time now. So the next talk will be given by Jordi Vegemans, and he'll tell us about guidable local Hamiltonians.
Yes, thanks for the introduction, Alex. Thanks to you all for sticking around on this day of beautiful beach weather. So this is based on joint work together with Martin Volkersma and Chris Kate that we published in the TQC proceedings. And this again will be a talk. There's some more implications, but I will mostly focus on the quantum PCP conjecture part. If you actually went to my talk on Tuesday, the slides might look vaguely familiar to you. So the quantum PCP conjecture is one of the biggest problems in quantum complexity theory. And in its local Hamiltonian formulation can be viewed as having a sum of k local terms. So our mission operators all only acting on a subset of k out of n qubits. And they're all normalized in the operator norm that are smaller than 1. And you basically have to decide whether the ground state energy of this Hamiltonian is either at most A or greater or equal than B. And now your promise actually that this difference between B minus A is lower bounded by some delta, which is a constant. So it's constant relative to the operator norm in this formulation. So the local Hamiltonian formulation from the PCP conjecture posits that this problem is in fact QMA hard. But this is a problem and not a class. And you can also define the quantum PCP conjecture in terms of actually a complexity class. And then you have a proof verification system where this all-powerful proof for Merlin sends you a polynomially sized quantum proof, but you're not going to use all of it. You're only going to look at the very small part of this proof using some randomness you generate by yourself. And then if it's a yes instance, then with high probability, there must exist a proof so that you accept with high probability. And for all no instances, we must have that for all proofs you will reject with high probability. And then the proof checking formulation posits that this class for some constant Q captures the full power of QMA. So this work is basically, we changed the story around quite a couple of times, but I think this captures the story pretty well. It can basically be viewed as adding some notions of classicality to both formulations of the quantum PCP conjecture. So similar as it's not really clear whether if you want to make a quantum generalization of MP, whether you need a quantum verifier with classical proofs or quantum proofs, which is the famous QCMA versus QMA question, you can ask the same question about, ask similar questions about the quantum PCP conjecture. So for the local Hamiltonian formulation of the conjecture, we will consider variants to local Hamiltonian problem where we assume some structure of the ground space. But the structure should be chosen in such a way that the problem not immediately becomes a classical problem. And for the proof checking formulation, we consider again a quantum verifier, but now you receive a classical proof instead of a quantum proof that you can access only a small part of. And so the main results I will present today are the following two for the following two formulations. Namely, for the local Hamiltonian formulation, we introduce a variant to the local Hamiltonian problem where we can actually show that in the high precision regime, so the one over poly n precision, the problem is QCMA complete, so it captures quantum hardness. But when the precision becomes constant, we in fact have the problem is in and p. So actually you lose the quantum hardness in this precision, in a different precision setting. And for the proof checking formulation, so for the quantum PCP with a classical proof, of course, if you check the whole proof, you will trivially capture the full power of QCMA. But if you only make a constant number of queries, then this class is actually contained in BQP that makes a single query to an MP oracle. We actually think or believe that it's unlikely to contain QCMA because it actually means that the quantum processing does not really use the proof in the way it's being processed. And so basically like the intuition we can get from this is that for that the quantum PCP conjecture seems to be brittle introducing these notions of classicality in a QMA where we don't know whether classical proof actually lose all the power of QMA in terms of the QCMA versus QMA question. But just to be careful here, like it's only specific, it only holds for these notions of classicality. I mean, you can also consider other versions of this. So now on to the technical part, how we get to these conclusions. So we study the following variants to the local Hamiltonian problem, which we call guidable local Hamiltonian problems. This can be viewed as Merlinized versions of the guided local Hamiltonian problem. And actually, this problem was already first introduced by Garibian and Legal 2 years ago. And you should really view it as just being the local Hamiltonian problem. But now you're given this extra promise that there exists a guiding state, which I will formally define later, that is some quantum state that has the promise of having good fidelity with the ground space of the Hamiltonian you're interested in. So the fidelity is actually lower bounded by some parameter zeta. And for the rest, it's exactly the same as the local Hamiltonian problem. And in this work by Garibin and Legal, the guiding states are sampleable states. And they're sampleable in the even tongue kind of sense, where you can both sample basis states according to the Born rule, as well as query the individual amplitudes on these basis states. And for our work, we actually consider a different class of guiding states, because one, we feel it's actually more natural for these local Hamiltonian problems. And two, if you want to talk about PCPs, this will be useful to actually design guiding states that will place the problem in NP, because we know that NP, of course, has the PCP theorem. So we say that the quantum state U is classically evaluatable if it satisfies the following two conditions. So one, there exists a classical description of U, which requires at most a polynomial number of bits to write down. And from this description, one can actually compute expectation values of log local observables using a classical polynomial time algorithm. And it's of course also possible to extend or generalize this definition to consider approximate versions. Then you would need randomized computation, and we do consider it in our work, but will not be very relevant for the remainder of this talk, except for the next slide maybe. And you can also extend this definition by considering quantumly preparable states, which basically means that there exists a unitary U which consists of a polynomial number of 2-qubit gates, or pick any finite gate set that's universal, that produces this quantum state with high probability. And actually in our work, you put a lot of effort into actually looking into all these kinds of different classes of states and whether they are actually quantumly preparable or classically evaluatable, comparing to sampleable states, have some theorems separating different classes. And if you're interested in that, please read our work. But for the complexity of these guidable local Hamiltonian problems, I already mentioned, so for the high precision regime, it will be quantumly hard. So we show from a locality already starting from 2, and in first polynomial precision, these problems are QCMA complete. So in the randomized reductions, when this overlap or this fidelity parameter is between 1 over poly n and 1 minus 1 over poly n, similar to what is known for the guided local Hamiltonian problem. And so the hardness actually drops if the precision parameter is only a constant. Or actually but here it depends also on the fidelity parameter. So if a fidelity parameter is also lower bounded by a constant, it's in NP. But if it's 1 over poly, it's in NQP, which is non-deterministic quasi-polynomial time. But we also think it's unlikely that QCMA is contained in that class. So it's still, to us, a very interesting result in the sense that it should not be quantumly hard. And I will not go too deeply into the key ideas of the proof of the QCMA hardness, but those familiar also with the guided local Hamiltonian problem, we really start from that proof, but there are some obstacles one has to overcome in getting to these results. Because in the BKP setting, you don't have a proof, which you do have, of course, in the QCMA setting. And really the key idea is to use the small penalty clock construction by Despande and others, co-authors, where you use the circuit Hamiltonian mapping, so the Feynman-Kitaev circuit Hamiltonian mapping, which you add a very small penalty on the H out term. And then it gives you actually very fine control over the Hamiltonians being produced in the reduction. So I sketch here a bit of what we do, but the most important thing is actually that we have 3 control parameters in our reduction. So the way we apply error reduction to the circuit, the way we use pre-idling on the circuit, so we add identity gates to the circuit we reduce to QCMA circuit to go to the Hamiltonian, and a small penalty parameter. And by using all these 3 control parameters, we have very fine control over the energy bounds. So on the left here, you see basically the witness spectrum. So on the y-axis, acceptance probability, and the blue regions are basically witnesses. And then eventually you end up with an Hamiltonian, where actually, so we isolate here a single witness by using unique QCMA, and we have very fine control here over the low energy spectrum in this fine Hamiltonian. So we know about the spectral gap and also if with energy bounds. And this is all very nice in using all the machinery that was used in the guided local Hamiltonian problem to get eventually to the result. So our work, but also actually the works before, have this implication to heuristic state preparation. Namely, if you consider in a fault-tolerant setting how one could potentially do quantum many-body physics or quantum chemistry, it's often proposed that one should adopt the following strategy. So we use classical heuristics to actually find a good guiding state. So this is all done without using a quantum computer. But then this guiding state should have good overlap with the actual ground state or state of interest. And then you use the power of quantum, namely quantum phase estimation, to project onto the ground state once you've prepared this guiding state on a quantum computer. And so basically a corollary of our results, but also I guess the previous results, actually that doesn't really matter if you, from a complexity theoretic perspective, if you use classical heuristics to find these trial states or use quantum heuristics. For example, adiabatic state preparation or variational quantum eigensolvers. As long as you have access to quantum phase estimation, it will lead both to capturing the power of QCMA. But of course, in practice, there might still be a lot of utility to using these quantum versions or quantum heuristics for state preparation. But all we know that for a complexity theoretic perspective, there's not going to be a difference in power. So for NP containment for this low precision regime, we actually use the deterministic dequantization of Lin and Tong's ground state preparation algorithm. And it is actually very simple. So consider the projection on all eigenstates of the Hamiltonian that have energy below A. And then the procedure is very simple. Just apply this projection to this guiding state U and compute the norm of the resulting vector. So in the S case, you must have there exists a state actually where this value is non-zero, and actually is lower bounded by this fidelity parameter. And in the no case, then for all states, this will actually be zero. However, of course, if you could simply implement such a projector, we'll be very happy, but you cannot do it in general. So the idea is to actually approximate such a projector by a polynomial in the Hamiltonian H, which is a trick that is used in many different places in Hamiltonian complexity theory and also other places. And then these polynomials in H of degree D generate actually a sum of KD local observables. So this norm of applying pH to U, the resulting vector, will be a sum of expectation values. And by our definition of what it means to be classically evaluatable, we can actually evaluate this norm. And then one has to be careful about the errors that are introduced by this approximation, but it will all turn out to work well in the end. So this was basically the general ideas behind the results we have for this variant of the local Hamiltonian problem. So let me now shift gears and move on to this quantum classical PCP we define. So really you should view it as having a quantum verifier with local access to a classical proof or restricted access. And the definition is really what you would expect. So as a class, we define this QC PCP Q, and the promise problem is contained in this class if there exists a polynomial time quantum verifier phi, such as for yes instances, there exists a classical proof, such as if you make Q queries or like you read Q part of the proof, then you will accept a high probability for some proof. And in the no case, then for all proofs, you will reject a high probability. And also we show in our work, so if you came to my talk on Tuesday, we actually also noticed now for a general quantum PCP, also here use a different kind of proof technique to show that non-adaptiveness does not matter for constant number of queries. Just the regime we are interested in. So this definition is in that case fully general if you only care about a constant number of queries. So our main result here is to show containment in the class BQP that makes a single query to an NP oracle. And here we state the theorem. So for any constant Q, it will hold. And the proof of the, again, it uses a similar idea to what I presented on yesterday. So the idea is basically that this CPCP Q verifier for a certain input X actually induces a Q local diagonal Hamiltonian problem. So there's a quantum reduction that you can do to learn this diagonal Hamiltonian. It will succeed with high probability and also the approximation. So in terms of how close eigenvalues are to the acceptance probability, there will be some epsilon, and that can be done in polynomial time in this 1 over epsilon. And then the reduction is actually very simple. So you have to perform this reduction using the power of BQP, which you have. Then the diagonal local Hamiltonian problem is in NP. So you make actually a single query to the NP oracle to solve the corresponding diagonal local Hamiltonian problem. And then again, one here has to be careful about the errors introduced into the reduction, but it will all work out fine in the end. And like what I mentioned already before in the introduction, we believe it's unlikely that QCMA is contained in BQP that makes a single query to an NP oracle. So we believe it's unlikely that this class can actually capture the power of QCMA making quantum number of queries. So we believe that this gives some intuition of why a quantum PCP would really have to use the power of quantum proofs. Our work also has other implications to the general quantum PCP conjecture. And the first one actually is that if you consider a quantum gap amplification, so for those familiar with the Noor's proof of the classical PCP theorem, a quantum gap amplification procedure would consist of starting with an Hamiltonian with an inverse polynomial promise gap, and you would apply some kind of mapping to reduce another Hamiltonian, which is a constant relative promise gap. We actually show that such an amplification procedure cannot preserve this property of classical availability with the ground space up to any constant or inverse polynomial unless QCMA is contained in MP or is contained in NQP. And it's actually very reminiscent of this work by Alex here and Dorota Haranov, where they have a similar result regarding stochasticity. So they show if a reduction like this would preserve stochasticity, then you would actually de-randomize MA. So MA would be equal to MP. And actually, the thing here is that actually many known gadget constructions actually do satisfy this property. And this is precisely what we actually use also in our proof of QCMA hardness, but also in the guided local Hamiltonian problem to be actually able to use these gadget reductions to get all these results in these improved parameter regimes. So two, our result also gives evidence that there cannot exist a classical reduction, or actually we proved this. So there cannot exist a classical reduction from a quantum PCP verifier to a local Hamiltonian, so that the eigenvalues of this Hamiltonian directly encode the acceptance probabilities of the QPCP verifier. So I explained the reduction on Tuesday, and actually if this reduction would behave in the same way, but then classically, then you could actually show that BQP is contained in MP. So there could still exist a classical reduction, but then we would have to behave in a very different way from the reduction that we know now. And finally, we also define a generalization of the NLTS theorem in terms of the NLCES conjecture, which is basically just NLTS, but then for classically evaluatable states. So remember this big picture that I showed you before containing all these relations between different classes of states. Quantitative quantum circuits are contained in the class of states that we propose. So this is a much bigger class of states you would have to prove lower bounds for. And also our work implies that you can even not have like one over poly overlap with these states. So it's even like a stronger version than just making the state. We also have some open problems that are left. In fact, we have many open problems, but I will only list 3 of them. So of course, this has been also mentioned before in many other places. So now we only know a lower bound on the complexity of quantum PCP as a class. So as a class, as being that it contains BQP and MP. So at least in the union of BQP and MP is a lower bound on the complexity of the class. But it would be nice to find a non-trivial lower bound, for example, MA or something else, on the class, on the power of quantum PCP. Further, so we would also like to do further study into these quantum classical PCPs we define here. And in fact, we have actually many improvised results now lying around. So if you're interested in this topic, have a chat with me after this talk. I can share some of them. And also, in the appendix of our work, we actually also consider many versions of our result, but then in the setting for MA. And one big open problem here is actually whether you can actually show MA containment of a guidable version of a stochastic local Hamiltonian problem, which we also don't know how to do. That was basically all I had to say here, and thank you for your attention.
Questions?
So you define the classical guiding state to be a classically evaluatable state without randomness. So what do you think will happen if you generalize the evaluatable state to the classically evaluatable with randomness?
Sorry, what?
So yeah. So you define you give a promise that the classical guiding state is classically evaluatable without randomness. So what do you think will happen if you can consider state with evaluatable with randomness, so in the constant promise gap regime?
Yeah, so for hardness, basically, of course, nothing changes.
Yeah.
And
Maybe
for-
so the
for-
containment in,
Yes.
in the containment in NP might not hold.
No, of course,
Yeah.
containment, but no longer hold
Yeah,
for
maybe
MD, because you-
contained in BPP.
No, it will be contained in MA. So basically, if you have a sufficient good epsilon, then it should be contained in MA. Like really by the same ideas that what you would do for in the MP case. Yeah.
Oi? Ainda tem tempo.
Passando automaticamente. Espera um pouquinho.
So now we have the last talk of the day. So we have Pedro Costa telling us about quantum algorithms for nonlinear differential equations.
Thanks for the introduction. Yeah, today I'm going to talk about our further improvements for quantum algorithms for difference equations, ordinary and partial difference equation. This is a joint work with Philip, Mauro, and Dominic Barry. Both of them are here, Mauro and Dominic. And the archive number you can also see here if you want to see more further details about this work. See how this works. Okay, yeah. So why do we care about this problem? Because we do care about this problem in several practices in industry, for instance. In the aerospace, you can think about the application in Navier-Stokes, nonlinear difference equations. You can apply that in finance, in stochastic difference equations. And also, for instance, another example is the oil and gas exploration that you can use, for instance, the wave equation. This is the outline of this presentation. I'm going to talk a little bit about early results and our contribution for this problem, and then followed by the background on Kalman normalization, and then we're going to move for the rescaling of the Kalman solver, and then talk after error bounds of the rescaling solutions, and then solution of the time evolution part, and then we're going to see the application for the PD problem. We finalize with the conclusion. So you can see the PD has the main application for quantum linear system algorithms. The reason for that is when you have difference equations that you don't have analytic solution, you have to come up with some ideas of discretization, like finite difference method is one of them, and you're going to end up with a large system of equations to solve. And as you know, there are a lot of progress made in this area of quantum linear algorithm solvers, starting from HHL. And 2021, we released our results, have the optimal results in the two parameters of the main parameters of the complexity, the condition number, and the allowable error in the solution. And you saw now earlier on in this conference that you also have now new results that get a kind of shortcut to get these optimal results. Now, I mean, the way it's going to be about it, actually the constant factors of the optimal results in terms of scaling, and which algorithm is going to be more practical in terms of apply the application, the implementation. So what is the challenge to solve these nonlinear problems on quantum computation? It's just because, like, you know that the quantum mechanics is a linear theory. Oh, sorry, not hearing me well? So, okay, thank you. And then you can cite a few early results for this attempt. For instance, there's one in 2008. They try to overcome this nonlinearity part by just doing multiple copies of your state. And you are to create this nonlinearity, but they end up with a larger complexity. You also have results that based on the nonlinear Schrödinger equation, that also they have come up with some ideas of linearization. But it looks that the most successful results are given by the Kalman normalization methods, that the one that are going to be focused on here today. And this is our contribution in this area. So you show how the higher order methods for the discretization for the partial difference equation is really be important in practice because you're going to see that it's going to be a bit problematic in terms of the stability of the solution. And you also show much tighter bounds for the error due to the Kalman normalization part for the ODE case, and also extend that for the PDE. And then you show the rescaling, the importance of the scaling of this problem in order to boost the probability of success to extract the component that interest after you apply the ODE solver there. And that's the problem we're going to do here today. Going to talk here. We're going to solve. This is the type of ODE problem, the nonlinear problem. This is a dissipative ODE. And remember, here we're talking about a set of ODE system problem, or you can think about a vectorial type of ODE problem. And is really important to have this quantity R that we're going to be talking later on as well in the presentation should be smaller than 1, because when you are dealing numerical methods, you also have to make sure that your solution is stable. The idea that when you come up with some approximation methods, you don't want to see your error blow up in time. And then we're going to see the application for the PD problem here. So there's the work overview here, the idea, the steps they're going to follow. So the idea that we're going to start with this set of ODE problem, nonlinear problem that are going to work. And then you're going to show the needed of the rescaling. So we're going to do the rescaling of this. And then we're going to go for the Kalman normalization. Once you have the cardinalization, you apply methods for solve this, or the solvers, and then you show how to extract the component of interest. And the same steps can be followed starting from the PD problem. So you start with the PD, a scalar PD, and you do a spatial discretization of that, and you end up with ODE now resulted from this PD as a set of ODE resulted after the after the spatial discretization of your PD. And you follow the same steps, but we have some issues, particularities there to make sure that solution is going to be stable. So we're going to be talk about now the background of the cardinalization. Is a bit technical these next slides, but the concept is quite simple. Let's see if I can explain that in the next slides for you. So the idea of the cardinalization is that you're gonna create new variables in terms of these powers, in terms of chronic powers, because I'm talking about vectors, these powers of the initial function that you have. And you created this like this y vector in terms of the previous elements of the functions. And then that's pretty much the idea that since I'm dealing with the first order ordinary differential equation, we're gonna see how this, we're gonna have to apply the derivatives of that. You wanna see that with the connection with the OD prime that we are trying to solve. So that's the part that you have to try to do the identification with the problem. And then you can rewrite all these equations in terms of the new variable. So the new variable now is y's, right? So now you see that you have a set of OD problems to solve. But be careful here, because now we have these terms are coupling. So we're going to end up with an infinite set of OD to solve. But of course, we are dealing with numerical methods. So we're going to come up with some truncation. And then we're going to end up with this Kalman matrix that we call it. This is the type of homogeneous OD that we're going to solve. And this matrix is a block matrix, like each component inside there is a block matrix related with the F1 and F1 components, FM components. And so the idea, so since you are dealing with a method of approximation, the idea that you want to try to enlarge this Kalman matrix in order to get a more accurate results, right? You want to make sure that you're going to have a semi-stable solution with that. So now we're going to show why you need the rescaling, why this is quite important to have the rescaling. So this is the standard way how we can encode the states that like you have this same idea, the same picture for the linear system problems. The idea is that the solution that you think each element of your vector has amplitude of probability in your vector state, right? So if you have a vector of size n, you're gonna need just log n qubits. So that's pretty much the reduction, exponential reduction in space. But here, remember that you are dealing with these y components now, y vector. So now each element is gonna be now this tensor, so the Kronecker product, so the powers of the previous function, the function u. And then if you look at that, the norm, if you have to actually normalize this, you're gonna see that pretty much that the first component, that the one that I'm gonna extract at the end, you're gonna be suppressed. Like, well, of course, that the norm here should be, the norm of u should be larger than 1. You're gonna be suppressed as you have more terms in the Kalman matrix, right? So you see that you increase the Kalman matrix in order to have more accurate solutions, but you're gonna end up with a higher number of amplitude application part in order to start the solution. You're gonna increase the complexity of your problem. So how we can deal with this? With this rescaling procedure, you have to rescale your OOD problem, and we're rescaling here, we call it by this gamma here. And then if you certify that the gamma is at least equal or larger than the U in, which U in is the initial condition for the OOD you are dealing with, you can certify that the probability is not going to be larger than 1 of n, where n is the Kalman order of your matrix. So that's a quite important part of the order to speed up the algorithm. Now we're going to see the error bounds on the rescaled solution. So I'm not going to go for the steps to get that, but pretty much showing, I'm just looking here, the first component of the y vector there, because that's the one I'm interested to look at. They're going to extract where the solution is. And you see that here, the importance to have the R, remember about the R quantity, is smaller than, if you guarantee this R is smaller than 1, you can guarantee that the solution is going to be stable here, not going to blow up in time in terms of the Kalman, also have the Kalman linearization. And then this is pretty much the standard technique. So the idea that here we just have to fix a target error for this after the Kalman approximation, and then we're gonna see how many, what is the size of the matrix we're gonna need it for a fixed error, target error of the Kalman part. So then you see that the order of the size of the matrix, but now we don't care too much about the probability of success to extract the component that are interest because you have done already rescaling. Okay, now we're gonna go for the solution of the time evolution part. So this we use the previous results that based on techniques for solving ordinary differential equations based in truncated Taylor series. You have some previous results that use the Ford-Euler technique. The idea that this technique of Euler method, for instance, is that discretization in time, and that's going to be not that accurate in terms of order of just the first order in time approximation. And here we come up with we just use the previous results in terms of the Taylor series, and then you also this is pretty much going to end up with another system, a linear system problem to solve, a large system problem to solve, where each V here represents a short time evolution using your truncated Taylor series. And then here that's the part that you're gonna apply your quantum linear system solver. And in particular here, I'm not working with the homogeneous. This example is an inhomogeneous case, but you can then get away of this F1s in the right side. Okay, so and also you can easily get the upper bounds with the arrows. So like you can see that again for a fixed target arrow in the for the approximated solution and the desired solution. And you can see that the number of terms of the Taylor series are going to be logarithm 1 over epsilon. And actually, it's logarithm over log 1 over epsilon. And okay, now I talk about the stability condition when you start with the nonlinear case, and then you do the cardinalization. But you have also to make sure that you're going to have your solution for the method of ODE solution. It has to be stable. And the way to look at that is by looking this eigenvalues of this emission part of the matrix. They call it that by the logarithm norm. So if you make sure these values are smaller or equal to 0, you can guarantee nice bounds for your discretization or your approximation method. So, but remember that you have done the rescaling procedure, and then by doing the rescaling procedure, you have analyzed it, and then make sure the eigenvalue is not going to be larger than the 0. And then get extra constraints, for the type of rescaling can be done there. And that's a bit of a restriction that you have when you have to make sure that you have a solution is stable in your ODE. And then you also can get nicer bounds when using this the gamma, the rescaling, for the lambda factor that you have to do for the blocking coding is pretty much the strategy using the blocking coding of the Kalman matrix. And you're going to end up doing the blocking coding of the operators F1 and Fm. But you can get away of the needed to express the lambda of Fm. So then we just plug that in the results for the ODE system problem that you have, and you get that complexity. And these we can compare with the results that are similar, the results that I have from 2023, but they only consider the order of nonlinearity equal to 2. And for us, it's arbitrary. And see that there they have this polynomial dependence in the Kalman order and a polylog dependence over epsilon. We don't know exactly what the poly order is, so it's hard to give exactly the speedups that we got here. And they have a bit of issue about the in the linearization, in the cardinalization method, because you see that the number of terms of n is gonna blow up if you have the u in, so the norm of the initial condition equal to 1. And then you could get away of this issue here. So now finally going to go for the application for the PD problem. So it's reaction diffusion problem, as I mentioned at the beginning. So this is a scalar PD problem, and then we're going to do this spatial discretization. But here we apply a higher order method for discretization. Here I'm considering the higher order in terms of K here. That means that the order of spatial discretization, and D is related with the dimension of the lattice. And then once you do this spatial discretization, you're gonna really find it really easy to identify with the matrix F1. And it's also not difficult to identify with the what is gonna be the components of Fm, the matrix, after you do the discretization, consider the part of B. And for just to make the calculations like simpler, and we just consider our analysis, the case where we are dealing with the periodic boundary condition for the Laplacian operator. So to have nice expressions to express analytically in terms of the eigenvalues and get the nice upper bounds for the norm of F1, which is here. Then we can express, this is pretty much the results from the norm of F1 that involves the Laplacian operator. And then again, you can just plug these results in our ODE problem once you have the PD, the ODE result from the PDE. And here we can compare with the results also from 2023. They apply exactly, they did the caramelization for exactly the reaction diffusion that we have done, but there they apply the other method, the four-ordered method, and they haven't included the rescaling. So you see the really bad dependence in the power of n here in U in. So you have the exponential reduction for us. And also they have a worse dependency in the total time, there is square. And in our case, it's just near linear. And this is pretty much the result because we are dealing with the Taylor series method for the OD problem, how did for the method. But here you have to have extra careful about it. Remember about R quantity that I said at the beginning. So you want to make sure that the solution is going to be stable once you do the linearization. And here, this BC comes from the norms of the FM and the maximum eigenvalue of F1. But here you have the issue that once you get the ODE from the PDE, the norm of the U in gonna increase, gonna be proportional in terms of the discretization points that you use it. An idea that you wanna in numerical methods, the idea that you increase the number of grid points to have more accurate solutions. So it's gonna be really limited the number of grid points you can use it. This shows the quite importance of to use the higher order methods, because you can see here for a fixed error for the discretization for the PDE, you can do kind of a trade-off between the size of the matrix and the sparsity of the matrix after the discretization in the lattice. So this shows that this could be quite relevant in practical for practical applications of the quantum algorithms for nonlinear equations. And another alternative way to have a guaranteed stability condition is consider the analysis of the U in, so the maximum norm of U in. And because the reason for that is because this norm doesn't depend on, not going to depend on the number of grid points used. However, we're going to have a rescaling now that is not going to be good enough to guarantee the probability of success higher at the end. Going to be suppressed again. We're going to end up with a suppression in the component that we are interested. So that you have a bit of have to be a bit extra careful when you are dealing with the nonlinear PDEs in the quantum computers. So now I finally get in the conclusion of the talk. So you did the rescaling of the original dynamics. You apply the truncated Taylor series for the time evolution part. You then consider the higher order method for the spatial discretization of the PDE. And you got really nice starter bounds of the error in the caramelization part. And next, you could try to devise a method less restrictive in terms of the linearization part, because this caramelization is quite restricted when the nonlinearity in the function, in terms of the function. But you, like if you want to apply, for instance, for Navier-Stokes, you have the nonlinearity is in terms of the derivative of the function. So that you should maybe try to come up with a new strategy for linearization. And another issue that you could do it, another thing that could move in that direction is do a further analysis in the stability. There's a reason for that is that all this analysis have been done, you are doing that, make sure that actually what happens that the entire solution, the entire vector is stable, but you are just interested in the first component. So maybe you can just look for a strategy to get a stable solution only for this particular subspace. And that's all for today. So thank you.
Questions? I have a very naive question. I'm not from this field. So, like here, what do you have any guess of what's the, like, do you have a good lower bound for how good the algorithm could be? Like using this, like less restricted quantum algorithms?
Lower bound, you say?
Yeah.
No, we don't have.
Okay.
I mean, you have the lower boundary related to the linear system solvers. That's going to be pretty much the part with the subroutine used there. So that's going to be also be important to get the total upper bound for the entirely solution.
Do you have any estimates for the space and time complexity of the algorithm that might be needed for the Kalman linearization procedure? What I mean by that is, compared to standard discretization procedures, do you need more qubits or more gates to run the algorithm?
Sorry, I mean, you're talking about in the OD case, the overall complexity, or you're talking specific about the resource estimation?
Yeah, resource estimation.
So the resource estimation is like still open questions here. So you don't have resource estimation for in general for difference equations on quantum computers. So a lot of work should be done in this part.
Okay.
I think I saw a paper from a few months ago that did like an analysis of this Kalman linearization on some like fluid dynamics problem, and I think they used truncation parameter m equals 3 or something, and they had some argument that they only had to use a very small truncation parameter. If that were the case in some application, would like this lattice point norm situation not be as bad, or?
So this actually is a result we are trying to move for that direction as well to analyze. So I don't know if we are talking about the one that is then considered the Boltzmann-Latson.
Yes, that one.
Yeah, that's the
Yeah.
one. Yeah, this is quite restrictive. It's quite they use the caramelization, but they have to be restricted this type of Boltzmann-Latson, which there are further analysis they have to be done on that part to make sure that have nice guarantees there. But I mean, I didn't look that carefully in that part. So
you're saying that the specific case of lattice Boltzmann makes things simpler than the case that you consider in general, or is that?
I mean, make simpler in which sense? You mean like?
I don't know. I guess I'm just trying to understand how that particular resource analysis plays in with your results.
I'm not familiar with the strategy of Boltzmann-Latson, so it's hard for me to judge. Like, but I know that's restrictive because I have already talked with people in industry that apply the Navier-Stokes, and they say that Boltzmann-Latson is really particular problems they can use. So like you would go for finite element method or finite difference methods for this case. So you need a like different type of strategy for the linearization.
I see. Okay, thank you.
Question?
I might just quickly comment on the lattice Boltzmann that the idea there is to deal with nonlinearities which are in the derivatives. So in this case, we have the derivative is a linear part, and the nonlinearity is in just something not involving any derivatives, and we need to have that the part which is dissipative is larger than the nonlinear part. So if you have a derivative that in the nonlinearity, and then you're doing discretization, then that discretization step can tend to blow things up. So the whole idea with the lattice Boltzmann is to get around that, because in Navier-Stokes you have a nonlinearity with the derivative. So the idea there is that they're changing things to a different equation to get away from that so that they can use the Kalman linearization. Well, it's a different type of equation, the Navier-Stokes than what's being considered here. Yeah.
More questions? If not, let's thank Pedro again.